today we'll be looking at the behavior of implicitly defined functions, and this first problem that we're going to do is really just a review of how to do implicit differentiation. So it's not exactly in this category, but it's just a little practice for something we'll need here. So if we're asked to find the derivative here, we are going to have to use the product rule here. So we'll have x squared times the derivative of y, which is dy dx, plus y times the derivative of x squared, which is 2x, minus, we're going to have to use the quotient rule here, put you some parentheses here. We're going to do low times the derivative of the high, which is 1, minus high times the derivative of the low, which is dy dx, over y squared. And this will equal 0. So what I actually would do here is I would take this whole thing and move it over to the other side. So that would give me x squared dy dx plus 2xy equals y minus x dy dx over y squared. And where I've got this y squared right here, I can multiply both sides by y squared. So that's going to give me x squared y squared dy dx plus 2xy cubed. And it will equal, these will cancel, so we'll just have y minus x dy dx. And so at this point we can move everything with a dy dx to one side, everything else to the other. So we're going to have x squared y squared. I'm going to go ahead and factor out the dy dx here. And then we'll move this x over, so we'll have plus x. And that dy dx has already been factored out, so I don't have to write it. And then on this side we'll have y, and we'll need to subtract this 2xy cubed, like so. And then the last step is to divide. And hopefully that is one of our answer choices over here. It looks like B right there would be our answer for number 1. Okay, so that's just a little bit of a review on implicit differentiation. Now let's look at the types of problems that we will see here in this section. So here it says, let C be the curve defined by xy equals -4. Which of the following statements is true of the curve at the point -2, 2? And so we're asked about relative minimum. We've got relative minimum, relative maximum, increasing and increasing, decreasing concavity sort of stuff. So for this case, we are going to have to use second derivative test if we're going to find a maximum or minimum, because whenever we take a first derivative, we can't really make a sign line when we're dealing with x's and y's. So we are definitely going to have to find the first and second derivative here. So first derivative, we're just going to use the product rule, x times dy dx plus y times 1 will equal 0. So x dy dx will equal -y. We'll divide by x there. So dy dx is going to equal -y over x. And if we want here, we could go ahead and plug in our point just to see what happens there. We've got -2, 2. And so if we plug in -2 and 2 here, we will end up with -2 over -2, which will give us 1. So my first derivative equals 1. That is a positive number. It's greater than 0, which tells me that the curve is increasing. Alright, this is not a maximum or minimum point because my first derivative would have to equal 0. So I could mark out A and B at this point. But I need to know about concavity, and for concavity, I've got to do the second derivative. So if I take this second derivative, I have to do the quotient rule. So I'll do x times the derivative of the top, which will be negative dy dx minus negative y, which will be a plus y, times 1 over x squared. And so I want to know this at negative 2, 2. So if I plug in xy, that should say xy equals like that, I will have negative 2 times negative 1. I'm pulling 1 up here from the first derivative, plus 2 over negative 2 squared. So I get negative 2 plus 2 over 4. Sorry, this is a positive 2. So I get 4 over 4, which is 1. If I have a positive second derivative, that tells me that my function is concave up. So C would be my answer. Alright, let's look at our next problem. It says, consider this curve. It is giving us our first derivative and our second derivative, so we do not have to find those. We don't know which of the following statements is true about the curve in the fourth quadrant. So in the fourth quadrant, we want to know about concavity and y. So concavity, we know because of the second derivative. So we would want to throw out A and B from the very beginning because the second derivative is what tells us about concavity. So we really just need to think about what's going to happen in that fourth quadrant. So in that fourth quadrant down here, you have a positive x coordinate and a negative y coordinate. So if we have a second derivative such that xy is positive negative, okay, then we're going to have negative 81 over 16 times a negative cubed. And if we have a negative cubed, that is going to give us a negative in the denominator. So we will end up with negative over negative, which is going to give us a positive. If our second derivative is positive, we would know that our curve would have to be concave up. So C would be the answer for this problem. That one's a little bit easier because you don't actually have to find the derivatives. Okay. 4 says, at how many points on the curve, and it gives us, in the xy plane, does the curve have a tangent line that is horizontal? So if we're talking about the slope of the tangent line, that is our first derivative. So we would want to take our first derivative, so we'd get 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3 times dy dx would equal 0. So if I move, actually I'm going to do, let's move this over first. So 2/3 y to the negative 1/3 dy dx would equal negative 2/3 x to the negative 1/3 here. And then we would divide both sides by 2/3 y to the negative 1/3. So we need to simplify that because it's kind of a mess. The 2/3 actually are going to cancel, but that negative stays. So we would have negative x to the negative 1/3 over y to the negative 1/3. And here we can switch the x and y's because we can move these over to the other side to get rid of those negative exponents. So we end up with negative y to the 1/3 over x to the 1/3. Or we could write it like this, negative cube root of y over x. Since those are both cube roots, we could put that together. So we want to know where this tangent is horizontal. So if that's what we're looking for, we're going to take this derivative, negative cube root of y over x, and we want to see where that equals 0. So we would divide both sides by -1 to get rid of that negative. We could raise both sides to the 1/3 power to get rid of the cube. You can see so far we're just dealing with 0. And then in order for this to be 0, y has to equal 0. I need to know how many times y does equal 0. So I need to plug this. So we need to know how many times y equals 0, because that could be at one point or it could be at several points. So we're going to plug 0 back into the original function to see what happens here. So we'll have x to the 2/3 plus 0 to the 2/3 is going to equal 9. I'm actually going to write the x to the 2/3 as the cube root of x squared equals 9. So to get rid of a cube root, I can cube both sides. So I've got x squared equals 9 cubed. I'm actually going to leave that as 9 cubed right now, because if I cube 9, it's going to be a larger number that's going to be a little harder to deal with. And I'm going to square root both sides. When I square root both sides, I'm supposed to put a plus or minus. And then I can think of this as the square root of 9 to the 3rd here, which is just 3 to the 3rd, which is 27. So I've got at positive 27 and negative 27. This is going to happen. So my answer here would be C. And then here's our number 5. I actually meant to put on the homework, so I'm not going to do number 5. I'm going to go over here to the homework. Let me see here. And we're going to look at this. And which one was it that I wanted to do? I want to look at number 4. So given the curve y times 2 to the y equals x in the xy plane, for what value of y, if any, does the derivative of y with respect to x not exist? So we want to know where that derivative does not exist. So we need to first take the derivative. So to do that, I'm going to have to use the product rule here. I'm going to do y times the derivative of 2 to the y. It's been a while since we did this. It is going to be 2 to the y times the natural log of 2. So that rule for exponentials that have any base other than e, it's going to be itself times the natural log of the base for that, plus 2 to the y times dy dx. And actually I need a dy dx here because that expression also had the y with it as well, and over here the derivative of x is just 1. So if I factor out my dy dx, I have y 2 to the y natural log of 2 plus 2 to the y equals 1, so I get dy over dx equals 1 over y 2 to the y natural log of 2 plus 2 to the y. And so this is our derivative. We want to know where this derivative does not exist. And so that's going to be anywhere that we get a 0 in the denominator. So we're going to look at that denominator, y 2 to the y natural log of 2 plus 2 to the y, and we're going to set it equal to 0. I can factor out a 2 to the y, so that leaves me with y natural log of 2 plus 1, and then I can set each one of these equal to 0. Alright, so 2 to the y is always positive. If you do log base 2 on both sides, you cannot take log of 0, so you actually don't get any answers from this first equation that we have here. Over here, we're going to have y natural log of 2 equals negative 1. We can divide by that natural log of 2. And so y equals negative 1 over natural log of 2. And we can see that that is our answer choice C, so we would choose that as our answer. So I hope this helps you. You need to finish the rest of this worksheet here for your homework, plus do number 5 from the one that was supposed to be notes. And we try something on every problem. We will look over these on Monday.